Today I want to present you our work on sampling optimized code for type feedback. Let us start with an introduction to JIT compilation. Let's look at this add function in R. The body of the function features the expression a plus b, and this function is polymorphic, so it depends on what kind of types you pass it. A different kind of addition will be performed. So let's say we could pass it 1 and 2. So a JIT compiler essentially optimizes this function by specializing the code that it produces to the types that were observed in the past. So if we look at this, we start out in an interpreter. The interpreter has the side effect of just keeping track of what kind of types were flowing through that function in the past. Then once we execute this function a lot, we will notice that, and the JIT compiler will kick in. We will compile a native version, and this one is fast mainly because we will specialize the code to the kind of types we observed before. So you might say, what happens if I pass something else here? What if I pass, let's say, tuples? So in this case, the types are not going to match what we expect. And something that we call a deopt is going to happen. The execution will transform back to the interpreter, and we can start recording the types anew. Once we execute this for a number of iterations again, the JIT compiler kicks in, we compile to native again, and we get fast again. Notice, however, that the performance doesn't reach the same level anymore, because now, of course, the function is generic and it will be specialized to scalars and also tuples. Now let us look at the exact opposite case. In this case, we start out by passing the add function scalars and tuples, and so already the first compilation event will emit native code that is specialized for those two cases. But now let's imagine our benchmark has sort of two phases. And in the first case, in the first phase, it's more generic. And then in the second phase, it becomes less generic. So for example, here it becomes monomorphic. Would we notice this? In a current JIT compiler, this is typically not noticed because of course the native code is supposed to be the peak performance output. And so it doesn't make sense to add instrumentation to this code that would detect such a case, but would also slow it down unnecessarily. So in essence, we're wasting this potential here, where if we would know that our program changed to a different phase, we would be able to recompile this to adapt it better to this new situation, to this new phase that we entered. So the problem essentially is that once we enter the last tier, the most optimized tier in our JIT compiler, there won't be any type feedback anymore because we want to avoid having any unnecessary overhead in that stage. As I mentioned, typically type feedback is gathered through instrumentation. So basically the code is annotated with some additional instructions which will keep track of all the kind of types that flow through it. There's another solution to gather type feedback. You could do sampling. The reason why sampling is usually not employed is that for type feedback we really want to be 100% sure. If we start optimizing code to the wrong types, then this will lead to de-optimization events. This will lead to excessive compilation. We will have to compile again and again until we get it perfectly right. However, if we already have a compiled optimized version, a compiled optimized function, we could use sampling to detect whether there is a likelihood of a situation where we entered into a new phase. So in a nutshell, this is our strategy. We start out with instrumented code that records type feedback in the usual way. Then we optimize, we get native code, say, and this native code will be specialized to the types that we have seen so far. So this is the typical idea of a JIT compiler. Then what we add to this idea is that at some point when the native code ran for a while, we will start sampling it. We will try to observe what kind of types we see there, and we will correlate those types that we see with the ones that we gathered in the instrumentation phase. If there is a big discrepancy and we think that somehow the program entered into a new phase, we will trigger a re-optimization event. This re-optimization will use the samples to augment the type feedback we initially gathered. If we got this wrong, then this will lead to a de-optimization, and basically this is what we want to prevent. So let's look at the approach in detail. We took the RSH JIT compiler, which is a JIT compiler for the R statistics language, and as I already described it before, this JIT compiler consists of an interpreter that records types and of an optimizer which compiles to native code. Now what we added to this optimizer, to the native backend, is a mechanism to extract the stack layout. So for every function, we need to know in which stack slot there is which variable. And in particular, we want to know what the original type feedback for that variable was. So in this example, let's assume we have a function which has 4 stack slots. In the first stack slot, there is something that we know is an integer. In the first stack slot, there is something that we have observed to be any kind of number. The stack slot number 2, we don't really know. And stack slot number 3, again, something that we have observed to be a number. Now, equipped with this stack layout, we can use a sampling-based profiler to scan the stack and look what's actually in there when we execute this. So let's look at an example of a run that could happen. For the first stack slot, we're not interested in what's in there. And the reason is that we already have a optimal representation for this. So integers can be represented in registers, so they won't even appear on the stack, or if they do, there is no better representation than just a machine integer for it. So no need to collect this type. In the second case, this will be a box number. And let's assume we observe that sometimes this is an integer and sometimes this is a double. So apparently there is no optimization potential here. This really needs to be a box number. In slot number 2, we record that the value is sometimes a double and sometimes a string. So this is more precise type feedback. But on the other hand, again, there is no representation in our compiler that optimizes for doubles and strings, so it doesn't seem like there is any optimization potential here. Looking at the third slot, or at slot number 3, something interesting happens here. Let's assume we recorded no integer samples and only double samples. So this suggests that we got the type feedback initially wrong, and that now only doubles occur, and that this type could in fact be narrowed down, and that we're using a too generic representation. So in that case, this will trigger a recompilation event, and we will feed back this type feedback, and we will overwrite the original type feedback that was collected in the interpreter with this constraint that now this variable is probably only a double. So in a nutshell, there's a 4-step strategy here. First, we extract the stack layout of the native code. Then we use a sampling profiler to collect the actual types that we find in those stack frames. And actually, we only collect the types of the topmost stack frames to reduce the overhead. And then the third step is that we look for discrepancies for stack slots which could benefit from a better representation. And if we find enough of these, then we'll trigger a recompilation using the sample type feedback. What kind of issues are we trying to solve with this? One example that we're trying to address is when we have type feedback pollution. So this happens if we have a function which is called from different completely unrelated call sites. A typical example here would be something like a MapReduce function, a higher order function where there is an API and different clients will use the same API with their own different types. And in the end, we will have a completely mixed up type feedback for completely unrelated contexts in that function. And so those types are typically completely useless. If we inline that function, say, we will drag in the type feedback. Sometimes we can statically avoid the pollution, but often we actually drag in the pollution by inlining. And so the sampling-based profiler would actually allow us to detect these situations and separate the wrong from the accidentally acquired type feedback from the actual type feedback. Another example that we found in R is that often programmers try to use integers, but they end up using doubles anyway. So here you can see that the programmer tried to use an integer indicated by the L suffix. So x is assigned to be the integer 1. But then somewhere later in the program, they will add a double 1 by accident. And this will lead to the variable being automatically converted to a double. And in the end, it's going to be a double for the rest of the program. So this happens quite a lot in R programs. A third use case that we thought about was interactive sessions. So let's say there is a global variable, and this global variable changes the type throughout an interactive session. We have an end-to-end prototype which is implemented in Nurse, and it detects these situations, and it runs with an overhead which is typically smaller than 10%, most of the time even smaller than that. What we didn't address yet is robust end-to-end heuristics. By that, I mean, if we consider this example from this diagram from before, then when we re-optimize and then the sampled information was wrong, we will de-optimize, and this can just happen all over again in a loop, and we should really detect these situations and have some heuristics that allow us to bail out in this case, and we didn't look into this yet. An interesting problem we had to overcome was how to trigger the samples. So we wanted to interrupt the program in regular intervals, and a problem that we had was that our programs can basically, so our libraries can come with their own C code, and also the R VM itself consists, of course, of lots of C built-ins, and each of those pieces, they can emit syscalls. And when you trigger, for example, a signal during a syscall, then many syscalls are aborted or restarted. So if you try to use a signal-based approach to interrupt the program during a syscall, then there is a danger of starving these syscalls. So we would have to mask the signal for all the syscalls, which is of course impossible because the packages can issue their own syscalls. So this was basically the first strategy we tried, and it didn't work. So then the second strategy that actually worked out really nicely was to use the PMU, the performance measuring unit that is present in most Intel CPUs, in newer Intel CPUs. You can configure it in such a way that it will notify you of certain events. It will trigger a signal on certain events, and as an event, you can use a retired instruction counter, but you can configure it in a way that it only counts instructions in user space. So this allowed us to robustly only trigger signals while we're executing in user space. One issue we encountered has to do with measuring the impact of this optimization. So here's a typical benchmark harness, and we start out by executing the benchmark a couple of times to let it warm up so that the JIT compiler can compile, optimize, specialize, and so on and so forth. Then we want to measure its peak performance, and for that we again run the benchmark a couple of times and we measure the average execution time. If we look at one of the measured executions, then assuming that benchmark has one of the behaviors that I described before. So let's say x first starts out as a number of any type, and then it narrows down to an integer over time. If our reoptimization strategy now suggests to recompile this benchmark function and to narrow down the type, then this is guaranteed to cause problems, because the way the benchmark harness works, the way we also benchmark normally in the SH, means that we will execute the same function in a loop over and over, so the same behavior is bound to repeat again at the beginning. So this methodology doesn't work for assessing the impact of this reoptimization strategy. Profiling optimized code and reoptimization, does it work? I don't think we have an answer how well this works in the real world, but we definitely saw a lot of potential with the idea. Normally, the VM flies completely blind and it wouldn't notice that a phase change happened and that a program is exhibiting more specific behavior. And this is a strategy that allows us to detect these cases, and we have demonstrated that in the cases that we imagined it would work, it actually did. I also want to say that this work showed us that we need a diversification of benchmarking methodology. So this strategy of executing the same code in a loop, it works for measuring peak performance, but there's other things that should be measured. I know there is strategies for measuring, for instance, say latency in a compiler, but the thing that we would want to measure for this work here would be something like end-to-end execution of one single program. Last comment I want to leave you with is that we think the PMU is underused in JIT compilers. There have been few works before us, and it certainly provides more capabilities that could be useful in the JIT setting.